All right, welcome back, class. Here we are, lecture 18, our second lecture in the series we're following on non-equilibrium fluctuations. This is a section very much unlike what we've done in the past half of this course. In the first half of this course, we thought a lot about perturbing a reference system by some small amount and asking for the leading order correction, the linear response of that system. We thought about that statically and dynamically. Here, this is the first sequence, the first little module in which we will begin really relaxing that assumption and trying to work out and understand the response of systems, dynamically or statically, to large perturbations, to perturbations that dynamically might drive them very far away from equilibrium or might generate very nonlinear responses. As I alluded to last lecture, and I want to reemphasize, the ways in which we tackle very nonlinear behavior are much more specialized than the way that we tackle linear behavior. Linear response has this beautiful framework in which everything is kind of situated and looks the same. There's a formalism that, independent of a lot of the details, whether or not it's an open system or closed, whether or not it's stochastic or deterministic, static or dynamic, the basic equations look the same. The basic insights of the relationship between Gaussian fluctuations and linear response all hold. When you perturb a system to a greater extent, when you generate nonlinear responses, the ways in which you try to tackle those systems are a little more specialized. They depend a little bit more on the details of what you're doing. And so over the last half of the semester, we will, through a sequence of different incarnations of nonlinear behavior, start to see that, start to uncover some basic guiding principles, even if they don't kind of fit all in a nice little box. So specifically in the context of driving a system dynamically far from equilibrium, doing some sort of time-dependent large perturbation to the system, we've introduced a couple technical tools which allowed us to derive some fundamental relationships last lecture. So today, I want to briefly review those tools, briefly review the results that we arrived at with those tools. And then the rest of the lecture really will be just to go through a very concrete example to see how this all works, to see how, for example, the Crook's fluctuation theorem emerges from an exact calculation of a system in which we do drive it arbitrarily far from equilibrium, but which is simple enough that we can work out things exactly. That will be a so-called driven harmonic oscillator, where we kind of know that owing to the fact that it is a linear system, things are analytically tractable. Okay, but to review first, last lecture, we introduced a complementary perspective on stochastic dynamics, that from its path integral representation. So rather than considering an individual stochastic trajectory as is generated by an equation of motion like the Langevin equation, and rather than thinking about how the probability distribution of those points along stochastic trajectories evolve, like would be encoded with the Fokker-Planck equation, we attempted to write down an object, the trajectory, an individual realization of a stochastic process, and assign a probability to that whole process, to that whole trajectory. So we denoted x, capital X of t, a trajectory, And what we meant by capital X of t was a huge vector of the configuration of the system at every point in time, up to some observation time here denoted t. It's a little bit complicated to write out because in reality, we can take this delta t that I've introduced to write out the components of that vector infinitely small, resulting in an infinitely long vector, a vector with infinite many components that, as we learned earlier this semester, was a functional. So you can think about x being a functional of t, or just think about it being a vector with an infinite number of components. So it's this object, the whole trajectory, the whole sequence, time ordered of configurations that we wanted to assign a probability to. Now, if this was a deterministic trajectory, provided the right initial conditions, that trajectory would have been generated with probability 1. A deterministic, a Newtonian, or the evolution of a wave function are done deterministically. If I give you an initial condition, it uniquely specifies the trajectory that's traced out. With a stochastic dynamics, this is not necessarily the case, owing to the potential for different realizations of the stochastic forces coming from the bath. This is the price we pay by opening our system up to allow for the exchange of energy with the surroundings, that our determinism, our unique trajectories now become stochastic, and thus for which we can assign a probability to. So we denoted the probability of a trajectory, capital P of x of t. That is the probability of observing the particular trajectory, x of t. And we worked out an explicit expression for that, which was simplified by the knowledge that our Langevin equation was a Gaussian process, that the probability of making an individual transition, x at delta t from x sub 0, was determined both by the deterministic force, where it would go in the absence of some noise, in addition to the probability of drawing just the right value of the noise that made that transition possible, that took me from the specific x of delta t from the x of 0 I started with. As the noise is Gaussian, it's then not surprising that the probability of observing the whole trajectory, it's a probability of drawing a sequence of Gaussian noises, and thus the whole trajectory has a Gaussian weight. Specifically, for an overdamped dynamics, one in which gamma x dot is equal to F, the deterministic force, plus eta, the random force, where eta had a mean of 0 and a variance of twice kBt gamma. The probability of drawing just the right sequences of noises to realize that trajectory is a sum of those specific realizations of the noise in the infinitesimal limit. That sum becomes an integral integrated from 0 to the observation time t. And substituting eta is equal to gamma x dot less F, we find the Gaussian functional that determines the likelihood of observing that trajectory. Now, I didn't last time name this. This has a name. This specific realization is something known as the Onsager-Machlup action. Specifically, that refers to the argument of that exponential. We have learned in other parts of this course that you can think about a dynamics from an action and time integral of a Lagrangian. This is a stochastic version of an action, and it bears the name of Onsager-Machlup because Onsager and his student Machlup were the first to write it down when they were thinking about Brownian motions and small departures from equilibrium. This is this concrete action for the overdamped dynamics, and it's not so hard to write out generalizations for the Langevin dynamics, underdamped, though it is a little bit more complicated, but still possible to write down a Gaussian functional. Even in the non-Markovian limit, it just becomes a function of two time integrals, like you might expect, because that Bath correlation function now extends over some finite amount of time. With this path integral description, we were able to prove a couple fundamental relationships, essentially just by interrogating the symmetry of this probability distribution. We made some really important connections between macroscopic thermodynamics, the laws of thermodynamics that were taught, and how these are resolved at a microscopic level, acknowledging that at such small scales, fluctuations are manifest. So specifically, we denoted not just the forward in time trajectory, but its time reverse counterpart. We called that x tilde of t. What we really meant by that was the arrangements of those configurations now in the opposite order. So instead of going from x of 0 to x of delta t, we're imagining going from x of delta t to x of 0. In general, those have distinct probabilities. If those two configurations were at different energies, that must mean that the likelihood of making the transition in the forward direction or the reverse has to do with the likelihood of having energy come from the bath into the system to allow for that excitation to happen. Indeed, because the bath is always at equilibrium at some well-defined temperature, it follows that the probability of observing a whole trajectory forward in time relative to its time reverse is just given by the heat that flows into the environment. This relationship is known as the Crooks fluctuation theorem. And tells us something deep about the nature of time reversal symmetry. In an equilibrium system where I'm not constantly dissipating energy, I'm not constantly releasing heat to the environment, the likelihood of seeing a trajectory in the forward direction of time or its reverse are equal. However, to the extent that there is a direction of time that I can tell a trajectory going forward from its time reverse, it must mean that there was heat released, that there was entropy produced. Indeed, this is a manifestation of the second law now made microscopic. It's a Jensen's inequality away from saying that heat always increases, or that entropy always increases. In fact, a concrete manifestation of this connection to macroscopic thermodynamics is to note that this implies that the probability of doing some work on the system relative to the probability of seeing that work released. So if I apply an external force to a system, I could increase its energy and thus do work on that system. However, in a fluctuating system, it is possible that the system over an individual realization does work on me. However, the likelihood that that happens is exponentially small in the amount of work being done, less its reversible limit. Then the reversible work is nothing but the free energy difference. If you think back to the simulation I showed at the end of last class, as I pull a polymer, as I extend it, I increase its energy. And in typical realizations of that process, it will indeed require energy input to affect that extension. However, it is possible through an unlikely thermal fluctuation that the system fluctuates into an extended conformation before I start pulling on it. And thus, as I pull on it, I'm extracting work from that system. The Crook's fluctuation theorem tells us that the relative likelihoods of those two scenarios are exponentially small. And in fact, when we go to macroscopic scales, work being an extensive quantity, we are essentially never going to see work being spontaneously created. This is further encoded by the Jarzinski equality, which is a sum rule that says that the exponential average of the work encodes exactly the free energy difference. That says that these fluctuations, the dynamics that may take a system arbitrarily far from equilibrium, still somehow encodes equilibrium thermodynamics. That if I average those irreversible processes in the right way, I recover reversible behavior. Indeed, another Jensen's inequality, evoking the convexity of the exponential, means that if I average e to the x, that is always greater than or equal to e to the average of x, which implies that the average work is always, sorry, these should be minus signs, greater than or equal to the free energy difference. That's Clausius's statement of the second law. The reversible work theorem, Jarzinski's equality, tells us where that inequality comes from. That there are microscopic processes that must allow for energy extraction. They're just exponentially rare. Okay. All right, so to understand these relationships concretely, to understand how one should think about work as a fluctuating quantity, and to see that indeed this fluctuation theorem is borne out, the rest of this lecture will be devoted to actually studying it in an exactly solvable system. So specifically, we will consider the work statistics in a driven harmonic oscillator. So being a linear system, this will be exactly solvable. We'll be able to see that with an exact calculation, the Crook's fluctuation theorem emerges, and what it means to say to be near equilibrium or far from it, what it means to generate a lot of work or little. The specifics, the game we will play, is to imagine that we have some harmonic oscillator with some potential, u of x, which through a coupling to the bath can undergo thermal fluctuations in this potential. And we're going to imagine driving this system through the application of some time-dependent protocol, lambda, from some initial lambda that for convenience will center at 0 initially, to some arbitrary final position. Oh, that's terrible harmonic oscillator. Like so. Now you can maybe imagine that if we did this very quickly, well, in fact, I can't, imagine that I did this quickly, started with a particle up here, did it quickly, so quickly that the particle stays pretty high up on the potential. I would have therefore raised the energy of that system, done work on that system by that amount. If I stopped it at that point, that particle would relax and dissipate that energy. So the mean energy between the two endpoints at long times will be 0. I'm just going to move the center of this harmonic potential. And thus the free energy difference under this protocol will be 0. However, individual realizations of the work, especially if I go fast, need not be 0. We will also see that it is possible that through a spontaneous fluctuation, the particle starts in a position high up on the potential in such a way that if I move the center of that minima, of that potential, I can extract work from it, though we'll see why exactly it is that that should be so rare. Okay, so that's the game. We're going to have a harmonic oscillator. We're going to imagine manipulating that harmonic oscillator through a protocol which changes the minima, the location of the minima of the potential. So associating equations with this, we have a time-dependent potential of the form kappa by 2. some spring constant, some stiffness of that harmonic potential, x less some lambda of t, which we will manipulate to afford different zero values of the potential. So this is our control parameter. And through its action, we will do work on the system. So thermodynamically, that's all we would need to know in order to understand work. However, dynamically, we, in addition, need an equation of motion. And let's assume that this particle in the harmonic potential is large and slow, moving around in a viscous solvent such that its equation of motion is overdamped. It satisfies the overdamped Langevin equation. There's some friction gamma. Rate of change of x is then given by the total force, which is minus the gradient of the potential, plus the random force with mean 0, and variance twice kBt gamma delta t. Again, even though we are imagining manipulating the system in such a way that we can take it far from equilibrium, the bath, relaxing infinitely quickly, stays at equilibrium with a well-defined temperature. You can think of this as a consequence of there being so many more degrees of freedom in the bath that can distribute any excess energy being pumped into the system particle, or slow colloid or polymer, in such a way that they are not so perturbed, the bath is not so perturbed from equilibrium. So by manipulating lambda, we can do work on the system. And we can write down that work as an integral from 0 to t, the work rate given by the rate of change of lambda, and how lambda changes the potential energy. So again, if I have no time dependence to my protocol, I don't do any work on my system. This immediately already tells you kind of what is meant by a stationary or quasi-static limit. It's where the rate of change of the parameter is slow relative to some time scales in the system. And we'll see that borne out shortly. Explicitly evaluating that derivative, we get minus k lambda dot and x less lambda. Remembering that u was k over 2, x less lambda quantity squared. It's worth rewriting this in a slightly telling way. We could add 0 in a creative way, such that we have lambda dot less x dot times x minus lambda. That's adding minus x times x minus lambda. If we subtract it back off, we have that. And now note this quantity here is the rate of change in the position with how the energy changes with position. That is the rate of heat generation integrated over time, gives you the total heat. Here, we have a total time derivative of u, including both the time derivatives from lambda and from x. Integrating that over time gives us the total change in potential. And so indeed we now see a microscopic realization of the first law, that the work is the change in the energy less the heat. Okay. So now we want to compute the work and understand its statistics. Its statistics are encoded in the stochastic realizations of x of t. That's the fluctuating quantity. Lambda is determined. It turns out it is useful to express x as a fluctuating part and a deviation from its mean. So let us decompose x of t, the trajectory x traces out, into a deterministic part and a fluctuating part. Such that x of t is equal to the deterministic part, call y of t, and the fluctuating part, call delta x of t. Those two dynamic variables each satisfy an equation of motion. Y dot of t is equal to minus k by gamma y less lambda of t, and delta x dot of t satisfies a similar looking equation, k by gamma delta x plus 1 by gamma eta. Indeed, if you sum the two, you recover the full equation for x. But now we've decomposed it into a fluctuating piece, delta x, that depends on eta, and a deterministic piece that depends just on the protocol lambda of t. It behooves us to note that kappa, or the spring constant, divided by the friction, has units of time, or inverse time. Y dot is equal to a number times y. That number must have inverse time units. And so let's define that as 1 over tau, the characteristic relaxation time of this system. Okay, so both of these, y and delta x, are first order linear differential equations. We can solve them with integrating factors, as we've done in the past. Thinking first about the deterministic trajectory. Y of t integrated, treating minus k of minus 1 over tau y as the homogeneous piece, we get a y of 0, e to the t over tau, the inhomogeneous piece, integral over t prime, t less t prime over tau, lambda of t prime. That's exact. Now let's make some simplifications without loss of generality. Let's assume that x of 0 is equal to 0. And as a consequence, y of 0 is 0. And let's set it up such that lambda of 0 is 0. This must be without loss of generality because the answer shouldn't depend on the absolute position in space, but a relative position where we end up relative to where we started. So without loss of generality, let's start at the origin with the control parameter lambda turned off. So the rest position of the harmonic oscillator is at 0 and coincident with its position. If that is true, this piece goes away. And it will behoove us in a little bit to rewrite the second piece in what will look like a bit of a complicated way, but which will simplify things. So note that d dt of e to the t minus t prime over tau is equal to minus 1 over tau e to the minus t by t prime over tau. And thus, this piece and this piece with a minus sign is the same thing as the time derivative of that exponential. And I can integrate that by parts and move the time derivative over to lambda at the cost of a boundary term. The boundary term at small time equals 0 is set to 0, but there is some boundary term associated with the t value, its evaluation at t. E to the t minus t prime when t prime is t is just 1. So we can rewrite y of t as lambda of t less the time integrals from 0 to t, e to the minus t prime over tau, lambda dot of t prime. This has a nice interpretation. Y of t is given by lambda of t plus a lag due to the fact that it takes a finite amount of time for y to relax. If tau was 0, e to the minus 1 over 0 is e to the minus infinity, which is 0. In that case, y would equal lambda. To the extent that tau is not 0, that second term contributes, and thus y will generically lag behind lambda of t. All right. Now for the fluctuations. We can integrate that equation in addition. Delta x of t, like y, will be given by an initial condition. This Green's function, now plus 1 over gamma, a time integral, a convolution of the Green's function, and now the random force eta. And now this is also kind of an interesting result. By construction, delta x is independent of lambda. In fact, there is nothing here to tell us that delta x is not an equilibrium trajectory. The bath, staying at equilibrium, still supplies the same thermal fluctuations. And so from the perspective of delta x, there is no difference between lambda being finite or lambda being 0. Delta x is a thermal or equilibrium variable, even though part of the system is being driven. This is a consequence of the linearity of the system, of the fact that a harmonic oscillator always responds linearly, that the fluctuations of a harmonic variable don't change. So this is specialized to this specific system, and essentially why we'll be able to solve this problem. Again, invoking our temporal boundary conditions. If x is 0 and y is 0, that means that delta x of 0 is 0. Simplifying this to just 1 over gamma and this time integral over the noise. Okay. So back to the work. In terms of our new dynamic variables, it's straightforward to write down the work. The work as a function of time is a time integral from 0 to t minus the spring constant, and now lambda dot delta x of t plus lambda dot y less lambda. Again, summing delta x plus y gives us x, and our original statement of the work up here was just lambda dot times x less lambda, exactly what we've just found, or just employed. Now note, the work, W, is given by an integral, fancy way of saying a sum, of x and y. So the work is linearly related to the fluctuating variables x and y. The work is a sum of Gaussian random variables. A sum of Gaussian random variables is itself a Gaussian random variable. That simplifies things dramatically. In order to compute the probability of a given work value, acknowledging that W is a Gaussian random variable, we need only compute two quantities, the mean value of the work and its variance, to uniquely specify that probability distribution. So we know the probability of a given value of the work. Let's denote it P of W. We know how to write that down in general. An average of a delta function always has an interpretation as a probability. I pick out 1 if that condition is satisfied, 0 else, and thus I'm summing up all the times that something happens, which is the empirical definition of a probability. Now remember, what we are averaging over are different realizations of this process. We're starting the harmonic system at the origin each time. We're driving it with a set protocol with a fixed duration. But with different realizations of that protocol, we will generate different amounts of work. There will be a distribution of work values. What we've just argued is that distribution is Gaussian, and so we can write down a general Gaussian form with some mean and some variance. Let's denote M of t, the mean value of the work, and V of t, its variance. So the mean is an integral minus k lambda dot. We have a delta x plus a lambda dot y less lambda. Bringing those averages in, delta x on average is 0. We can see that from its integrated equation here. Delta x is linear in eta. Eta has a mean of 0. The only fluctuating quantity in delta x is eta, and eta on average is 0. So delta x does not contribute to the mean value of the work. Y, on the other hand, is deterministic. It has one value. And so it contributes to the work, but its average is trivial. Its average is just its value. So let's go ahead and take its value. See if I can get all of this. All right, I'm going to miss a little bit. So the mean value of the work is minus kappa, integral from 0 to t, t prime, lambda of dot of t prime, and now lambda of t, the minus sign, plus y, which is all of this. Let's put this all on the same line. Okay, all in parentheses. All right, and now you see why we factor out that lambda to begin with. These lambdas then cancel. I have Now 2 integrals from 0 to t. So these need new dummy indices. So putting this together, the mean value of the work is minus k integral dt prime from 0 to t, integral dt double prime from 0 to t prime, lambda dot of t prime, lambda dot of t double prime, and a convolution of those with this Green's function dependent on the characteristic relaxation time of the system. So that's its mean. To go any further, we would need to specify exactly what we mean by the protocol. Its variance, V of t. Well, y is a non-fluctuating quantity, so it will not contribute to the variance. Delta x, however, will. So going back to the definition of the work, y is its average, so its fluctuation is 0. Delta x, while it has an average of 0, has finite fluctuations. So the variance will just be given by this quantity squared. Just realized I dropped this minus sign. That should be plus. All right, so squaring that, I have k squared, 1 integral from 0 to t, t prime, 2 integrals from 0 to t, t double prime, lambda dot t prime, lambda dot t double prime. And now the average of delta x of t, delta x of t double prime. So a correlation function. Let's clean that up a little bit. All right. To evaluate that, we need the correlation function. So what is the correlation function of delta x of t prime, delta x of t double prime? Well, exactly because delta x does not know about lambda, there's no lambda that determines its trajectories, that correlation function is independent of lambda, and thus we can work it out as an equilibrium time correlation function. If, for example, let's just do it here, delta x of 0 were not 0, we leave it finite for the moment, I can multiply both sides by delta x. Let's do this in another color. Can multiply both sides by delta x of 0, that squares that. And average, and again, the time translational invariance of this correlation function is valid because it doesn't know that I've broken time translational symmetry through the application of lambda. As before, x at 0 is not correlated with eta at t, so that term goes away. Delta x squared and averaged is just the equilibrium value of delta x, the equilibrium value of the position or the displacement of the oscillator about its minima. From equipartition, we just know what that's going to be. It's going to be kBt over k. And so we have a correlation function for delta x with a prefactor kBt over k and a decaying exponential. So we can pop that in down here. So KBT will come out. K will cancel one of those Ks. And now I'm going to rewrite that nested integral by including only half of its domain and multiplying by 2. So this is an integral that goes in t prime and t double prime from 0 to t. So it's over that square. I will include only the triangle and multiply that area by a Jacobian of 2. And that's okay, because that equilibrium time correlation function has that time translational invariance, and moreover is an even function of time. It is true, it is the same, it returns the same value when t double prime is greater than t prime, as well as when it's less than that. And now look at what we've just arrived at. Let's go ahead and get this little drawing out of the way and let me make this exponential a little clearer. If we look at the variance, it's 2 integrals over 2 rates of changes of lambda convoluted with that decaying exponential. The mean is 2 integrals over the rate of change of lambda convoluted with that decaying exponential. So in fact, what we have just found is that we would have been sufficient to have just computed the mean itself. The variance is twice KBT, the mean. The variance of the work is proportional to the mean value of the work in this case. And so the probability distribution of the work is uniquely determined just by its mean value. So putting this all together, we have P of W is equal to e to the minus beta, W less its mean, quantity squared. The variance is twice the mean, gives me 4 m of t. And normalize by its variance, twice m of t divided by beta. So that is the full distribution of work values. If we look for this symmetry as expected from Crooks, so those denominators cancel. I have in the numerator e to the minus beta W less its mean quantity squared divided by 4 its mean. In the denominator, minus beta W minus m of t. Only the cross terms will survive, and in the numerator that cross term is minus beta twice W m of t divided by 4 m of t. In the denominator, I get plus beta twice W m of t divided by 4 m of t. I can bring that, plus, minus. I can bring that upstairs. I'll have 4 m of t, which cancels in its denominator, leaving me just with e to the beta W just as expected from Crooks. So again, the probability of seeing the probability of extracting work from this protocol is exponentially small relative to the probability of doing work on the system with a scale set by that total value of the work. We can now understand a little bit more where this comes from, where negative values of the work come from. We are going to plot this. Imagine, if you will, a spontaneous fluctuation that takes the particle high on the potential, such that when I perturb that potential, say move it by this amount, now that particle is high on the potential, it will spontaneously relax, emitting heat, or allowing me to retrieve some energy, to extract work from it. However, as should be abundantly clear, the likelihood of having such a rare fluctuation that takes the particle high up on a potential is exponentially small. In the course of thermal fluctuations, that initial condition is exceedingly rare. Much, much more likely is that particle stays near the bottom of the potential, and when I perturb it, now I have increased its energy, made that particle very, very high in energy, and thus have done work on it. And indeed, the relative likelihood of seeing those two paths in which I move the particle to a location, move the minimum of that harmonic oscillator to a position where I can extract work, is exceedingly unlikely. Overwhelmingly, the particle will be in a position near the minima of the potential, and thus any perturbation away from that will increase its energy. I'll have to do work on the particle to lift it up to that height. We also see from the equation of the mean value of the work what it means to be quasi-static. So remember, the free energy difference between this harmonic potential and that harmonic potential is 0. Those are two harmonic potentials just moved laterally. So from the particle's perspective, the number of states, the number of thermally accessible states, the partition function in each of those static cases is identical. There's no change. I've not changed the curvature of those potentials. I've just moved where they're centered. So the reversible limit should correspond to this mean value of the work being 0. So how does that mean value of the work be 0? Well, there's a trivial answer in which I don't do anything. Lambda dot is 0. The alternative, however, m will go to 0 as tau goes to 0. If the system relaxes infinitely quickly, there is no domain over that integral. The value, the area under that 2-time integral becomes 0. It becomes so exponentially fast. So the reversible limit the limit which thermodynamically is imagined to be some idealization, when we think about it from the context of the actual dynamics of the system, we can make very precise statements. The reversible limit is where the rate of change of this protocol is small relative to some characteristic time scale. So in the limit that we are integrating so slowly that the system is able to keep up with that perturbation, we will recover the reversible work. What else to say? So if I imagine performing this protocol with a fixed speed, such that lambda was some fixed velocity times time. So I move this, the minimum of the potential at a constant velocity. That's lambda dot is just v. Then the mean value of the work is going to go proportional to v squared. I put two functions of v underneath or within this integral. I'll have a v squared, I'll have a k. And if I wanted to write it out exactly, like so. Can we do that integral? Let's go ahead and do that integral. So the first integral, so let's pull the e to the minus t prime over tau inside. That's a simple integral to do. And it gives me tau e to the t double prime over tau, evaluated at 0 and t prime, which is tau e to the t prime less 1, v squared k integral 0 to t prime. Minus t That cancels, that's just 1. And I have minus e to the minus t by tau. That gives me vk tau t less tau plus like so. So indeed, we find that as tau goes to 0, the mean work goes to 0, otherwise it scales like b squared. All right. Well, I think that's essentially all I wanted to say on that. So what we've done is just explicitly show that the Crook's fluctuation theorem holds in this exactly solvable model, and we got some insight as to what it means to do a large and fast perturbation to a system. In general, we will do work on that system, but the constraint afforded by time reversal symmetry means that there is information that is still encoded even in those trajectories far from equilibrium. So we will see next time how this results in us being able to make general statements about nonlinear behavior. And specifically, we'll think a little bit about the complement to the entropy production as manifesting the time reversal asymmetry of a system, and rather think about what it means to relate time reversal symmetric quantities to each other. The difference between the forward and backward directions of time are given by a heat or given by a fundamentally thermodynamic quantity that is a displacement. It's the displacement along the energy direction, the energy taken in from the bath. We'll find next time that the time reversal symmetric contribution to the likelihood of seeing an individual trajectory contains fundamentally dynamical quantities. And so we'll see how that manifests itself in providing some structure into non-equilibrium or non-linear responses. All right, but we'll go ahead and end early today. So I hope you all are well, and I'll look forward to seeing you all in the small group discussions this week. I think next week is spring break, so we'll be off, and then we'll come back and conclude our discussion of far from equilibrium behavior before we move into chemical dynamics. All right, all be well.